In the previous video, we have seen how you can create the VHDL project in xilinx vivado and how you can write the VHDL code and then create RTL schematic. Generate RTL schematic and generate block diagrams as well as verify the outputs using timing diagrams in xilinx vivado. So in this video, what we are going to do is we are going to create different components, and how you can use the components multiple times to create a logic function. So for this, we are going to use full adder using two half adders as an example. So we already know we can create full adder using two half adders as well as an OR gate. So we are going to do that design here. So first of all, let's open the Vivado. If you didn't watch the previous videos, you can watch them. I've said how you can create the project and how you can initialize the ports, how you can write the test bench, etc. in the previous video, which is the part 2. If I'm not wrong, it is part 2. So now inside the Vivado, we'll just create a project as usual, and I'll give this name as full adder using half adder. Next, and it is a RTL project. So next. Now for the sources, we will use two sources, which will be half adder and full adder. So in half adder file, we will write the logic function for half adder, which will be the sum and carry, which will the outputs of the half adder will be sum and carry, and inputs will be A and B. So I will create a half adder, and then we will create full adder. So this full adder will use two half adders. So we'll see the block diagram in this video soon. So we don't have any constraints. So I'll click next, and then I will go with the default device and then finish. And now it creates the project. Then we will define the ports. For half adder, we have A and B as inputs, and sum and carry as outputs. And for the full adder, we have A, B, and C as inputs, and sum and carry as outputs. Now I will click OK, and it will create the files and sources. So now what I'm going to do is I'm going to open the half adder file, and inside half adder file, I will just write the functions for sum and carry. So the sum of the half adder will be A XOR B, and the carry of half adder will be A and B. We already know these functions from DLD, digital logic design, or it is also called as switching theory and logic design. So we know the equations for sum and carry. So for the sum, it will be A XOR B, and for carry, it's A and B. Now let's open the full adder. And inside full adder, what we have to do is we have to initialize this component. This entity. In here, this is the top entity. So this is like the half adder is the top thing in half adder.vhd. But inside full adder, we will use this half adder as a component. In this half adder is a device in half adder.vhd, but in full adder, half adder is a component. So we will initialize this as a component. For initializing, we will initialize before the begin statement. So I will just go and create component, and then followed by the component name. The component name will be half adder. So half adder. So this name should match the entity name in here. So we have half underscore adder, right? So in full adder, when we are initializing a component, we have to use the same name, which will be half underscore adder. And now is port. Now we are going to give the ports. So A, which is input, and follows std logic. B, which is input, and follows std logic. This is a half adder, so sum, which will be output, and follows std logic. And finally carry, which is an output and follows std logic. And then we will end the component. And now we have the half adder component. Now we can save this, and we don't have any errors, so we can proceed. Now what we have to do is we will create the signals. So you might be wondering what these signals is. So signals are like the connections, like the lines or bus or uh, routing lines. So if we take the block diagram, you can actually understand it clearly. So in here, for the half adder one, we have A, B as inputs. But for half adder 2, we are taking the outputs of half adder 1 as input, which is S1. So we didn't define S1 anywhere here. So what we are going to do is this invisible line, right? This invisible wire, we call this as signal, and this one as well, and this one as well. So these ports we already defined while creating the project, right? So these will be visible for us, but this thing will be then IC. So inside IC we have these connections, which we call these as wires in Verilog, and we call these as signal in VHDL. So I'm going to define the signals here. Signal, we have three signals in here, so which will be S1, C1, and C2. So signal S1, C1, and C2. And we are getting an error here. Semicolon up the last interface is also support. Oh, I think it's just a warning here. Oh, we put the semicolon at the last statement, so we don't need to put this, because if we put this, we will get an error. So now we can see that the error is actually gone. And now all these three will follow STD logic. Now we have the signals as well. So now we can create the half adder instances here. And then we will use these signal variables uh, just I mean, we can assign these, right? So S1, C1, and C2, we will map the ports to other ports. Now in the begin statement, what we have to do is we have to create the instances, and we have to give the name for each instance. So for example, if I'm going to create an instance of half adder, I have to create a name for it. So I'll give the name M1 for the first instance, and then we can simply write like this. So it's like calling a function in programming languages. So you can simply write half adder, and for the but we are going to map the ports. So port map. So this thing actually initializes the half adder with the name M1, and we are going to port the names, map the port here. Just confused by this. So the port A of half adder will be A of full adder. So A is the A, B, C are the inputs of full adder. So and A, B are the inputs of first half adder. So I'm going to give these as A, and B as B. And now we have sum, and the sum of first half adder is S1. We've already defined S1 as a signal, so S1, and then carry of first half adder is C1. C1. And now we are going to instantiate this second time, half adder, port map, and now what we are going to do is for the second half adder, we can see that the first input is S1 and the second input is Cin. So here A will be S1 and B will be Cin, and sum will be, so the sum of second half adder is the sum, so direct sum. So I'm just going to give sum, and for carry it is C2. This is not the output of second half adder, right? This is the output of OR gate. The carry output of half adder 2 is C2. So I'm gonna give C2 here. And finally, the output carry of full adder is C1 or C2. You can see that in the block diagram here. We are ORing the C1 and C2 and we are taking that as output of carry. Now I'm going to save this. Let's see if we get any errors. Yeah, so we don't have any errors now. And you can also see that the file structure changed here. In before it used to be full adder, and then there used to be half adder down here. So they will now they will go into the half adder because we used half adder as an instance, and we named the instances M1 and M2. Now we have created the main file. Now what we have to do is we have to create a test bench. Now, for creating a test bench, I've already explained how you can create a test bench in the previous video. So I will create it directly here. Just make sure that you give a different name other than your source file name. So now the ports for this will be A, B, and C. Or you can actually leave this like this, and because we are going to comment them in the simulation as well. So now we have to go here and then we'll add a test bench. Now you can see that we have the default file and we have to write the test bench inside this. So for writing a test bench, we follow the same rule what we did in the full header. So we have instantiated the half header. We have initialized the half header component. So in test bench, we will initialize the full header as a component. So full header is the entity name here. So you can see that full underscore header. So in the test bench, we have to do this. And now is what it follows the same syntax. And now we have A as an input and follows std logic, and B as an input and follows std logic, and C as an input. So we are writing the test bench for full adder but not half adder. So for full adder, we already know that we will have three inputs A, B, and C and two outputs which are sum and carry. Std logic, and finally carry out std logic. And then we will end the component. I've already explained how you can write the test bench in the previous video. So if you didn't watch the video yet, you can go and watch it to know how you can write the test bench. Now, after this end component, we are going to create the default values for the inputs. So A, we'll just write it as signal A, and it follows std logic. The default value will be 0. I have already told how why you write these statements here so that you can clear all the ports and stuff. Cin std logic, and we are going to give 0. So these are the inputs. We are going to clear the inputs, and for the outputs we can't clear the outputs, but because they are dependent on A, B, and C. So we'll just write the output as they follow this std logic. So signal sum std logic. And now another one which is signal carry, which follows std logic. Now we have signals, and we have also initialized the component. Now what we have to do is we can simply write the test bench inside our begin. So before we write the test bench, we have to say which component we are going to put under the test. So we are going to put the full adder into the test. So UUT full adder, and we will map the port map. And if you take the full adder, we can see that we have A, B, C in as an input and sum and carry as output. So we will map the same things by taking these into consideration. So the A in full adder is A in test bench port, and B follows D, and C in follows C in, sum follows sum, and carry follows carry. So you can also do this without putting the port and map by like we do in the C and C++ or general programming languages. We can simply call this as a function, but this will be a better way, because if you have multiple variables and if you are confused which variable is which one, you can simply do this. Now we have defined the unit under test. So UUT stands for unit under test. I'll just write it here, unit under test. So we are going to test the full adder component or full adder entity, and then we are going to give the inputs and outputs. We have to map the ports. Now we are going to begin the process. Begin. So inside begin, we can write the truth table. But first of all, we are going to wait for 100 nanoseconds. We already know why we are waiting for 100 nanoseconds. I've explained why in the previous video. So if you watch the previous video till the end, you will know why we are waiting for 100 nanoseconds, why we have the initial delay of 100 nanoseconds. So if you don't know, watch that video till the end. So now we are waiting for 100 nanoseconds, and then I will just give the truth table. So 0, 0, and Cin will be eraser, and then wait for 100 nanoseconds. I will just copy this and then paste it down there, because we will have eight combinations, because we have three variables, and when we already know the combination equation, which is 2 power n. So we will have 8 combinations, which is 2 power 8, 2 power 3, because we have 3 bits, right? 3 variables A, B, and C in. So we'll have 8 combinations. So 1, 2, 3, 4, 5, 6, 7, and 8. And for the last case, we can just remove the delay. And now we will write the truth table. So first one is 0, 0, 0, and 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally 1, 1, and 1. So this is the truth table. We already know this. And now I'm going to end the process. End process. Now I will save this. And now we don't have any errors. And you can also see that we have a UUT of full adder now. Now we don't have any errors. So I will just run the simulation. Run behavioral simulation. It will take some time to simulate the results. So now it's simulated. And now what we have to do is we have to click this, and you can see the outputs. Now for the 0, 0 instance, 3 zeros instance, actually 0, 0, and 0. If I put the mark here, where is this mark? So if I bring this here, we can see 0, 0. For 0, 0, 0, sum will be 0 and carry will be 0. And for 0, 0, 1, if I drag this here, so we have 0, 0, 1. So sum will be 1, but carry will be 0. And for 0, 1, 0, same thing, sum will be 1, carry will be 0. And for 0, 1, 1, we will have sum 0, but carry will be 1. And then if we take the next instance, it will be 0, 1, 0, 0, sum will be 1, carry will be 1, carry will be 0. I dragged it, so okay. Now for the next instance, which is 1, 0, 1. So if we have two ones, the output will, the sum will be 0, but carry will be 1. So we have two inputs here, right? Two ones here, A and C in R1. So sum will be 0, but carry will be 1. In the next instance is 1, 1, 0. The same will be repeated here. Sum will be 0 and carry will be 1. But the final output, final thing is 1, 1, 1. So if you have three ones, we will have sum as 1 and carry as 1. Because the first two numbers, if we add these two bits, we will get sum as 0 and carry as 1. So, and then we will add sum and this cin. So 1 and 1 will be 1 and carry will be 1. So this is the full adder circuit, and if you run the linter, we will get the design. I mean the schematic, right? We will get the schematic. Now I'm gonna go open this here, and then if I click on schematic, it will show us the schematic of our logic. So it will take a little bit of time. It also depends on your PC. If you have a good PC, it will be faster. So this is the schematic. So you can see that we have used two half adders, when we have also given the names of first instance M1 and second instance M2. You can see this M1 and M2 here, and these both are half adders. And we gave the first carry of first half adder to an OR gate, and the carry of second adder to the OR gate again. And we are taking the output carry as this one. So if you click on this, you can see the internal diagram of this, which will be an AND gate and an OR gate. And if I maximize this, you can see. So both will be the same. And so now if you run this synthesis, okay, it will start this synthesis. We have already seen why we used these different things like RTL analysis and Y synthesis and implementation. And finally, we will get a generate bit stream when you connect the device. We have already discussed all these things in the previous video. So you can watch that video to get more knowledge on what these things are. So we'll see the synthesis part, and I'm not going to show the implementation part because we already know how implementation looks. Because when I click when we do the implementation, it will show you how it implements in the selected device. So we have selected the default device. So it will show how the implementation will be done in this device. I will only do the synthesis part, and I will stop the video. Alright, now I will click on open synthesizer design and click OK. Loading device. And there we go. This is like the how it will look in this device. So if I click on schematic, you can see it as a block diagram. So this is how you can create the modules, and how you can use the different modules multiple times. You can create a lot of modules here. We have only created this for half adder. There will You can create a lot more modules in here, and you can just uh, run your program. So this is it for the video, and thanks for the support so far. I'm not expecting this much support, and thank you very much. If you came to the end of the video, thank you very much. But don't forget to like, share, and subscribe, and then don't forget to view the previous videos, because if you don't watch the previous videos, you won't understand these videos and the future videos as well. So don't forget to watch the previous videos. Thank you very much.